So far the rectifiers we've looked at, or AC to DC converters that we've looked at, are uncontrollable. And what I mean by uncontrollable is that the voltage across the diodes is really what dictates when the diodes conduct, and therefore how the output voltage is related to the input voltage. And so, I mean, the DC and the AC voltages, speaking about outputs and inputs. But there are cases where you can create AC to DC converters that are controllable. I mean, you can have fully controllable. You can also have semi-controllable. Fully controllable would be using something like let's say a MOSFET switch, where you can control the on and the off instances exactly. But then you can also have semi-controllable, which are based on devices called SCRs, silicon controlled rectifiers, or thyristors, as they're known more commonly. So the two names are usually used interchangeably. But essentially what an SCR is, so the SCR is a semiconductor device. So basically the circuit symbol looks like a diode, except there's a third terminal here, right? So what you have is you have the anode, you have the cathode, and then you have a gate. And so the way that this device operates is if you have a voltage, let's say VAK, as we usually do, and you might have a current, we can call this, I don't know, let's call it IAK. And then you'll have another current here, we'll call this IG. So that's the gate current. So basically what the SCR does, or the thyristor does, is it acts like a diode, but it also has another layer of complexity where you have, or I guess another layer of control maybe, is it only turns on when you apply a gate voltage. And then once you apply, a gate current. Once you apply the gate current, it acts like a diode. So what does that mean? That means when you apply, let's say, a positive voltage here, the diode, or the thyristor will only turn on if you've also applied a gate pulse here. So you have to have both of those conditions satisfied. So it's not enough to just say I applied a positive voltage here and this should turn on. No, it won't. So you have to apply a positive voltage here, and then once a positive voltage is applied here and this gate is applied, then it acts like a diode. And so you can control how it turns on. That would be the turn on control. But the turn off control, basically you have to force the current down to zero, right? So naturally when the current goes to zero, because let's say you have an AC waveform, so if the voltage goes up and then all of a sudden it comes down and it crosses zero here, and then it keeps going like this, so at this zero crossing, the thyristor will turn off. And then if you want to turn it on again, in the next cycle you'll have to apply another gating pulse, they call them. And so you would have to apply some gate current. So what we're going to do in this video is we're going to look at these silicon controlled rectifiers, or thyristors, and how they're used in what we call phase controlled converters. We're going to focus mainly on rectifiers in this type of application. Although the rectifier and the inverter, you can kind of, just depending on the way you modulate them, you can actually have you can use the same topology for both, as we've seen in the cases of AC to DC, or DC to AC converters. We've mentioned that before, that all you really need to do is control how you modify how you control the switches, and what ends up happening is you have a completely different converter in that case. So let's take a look then at the half-wave controlled rectifier, and we've already looked at the half-wave controlled rectifier in the case of the diodes. So if you're not familiar with the half-wave rectifier, I'll link that video in the description so you can take a look at that. But the half-wave controlled rectifier with a resistive load, and again, this is a controlled rectifier, so it's going to make use of this thyristor. And what you have here is you have a resistor, okay? So you have a resistor here, you have we can call this thing Q if you want, let's say. You'll have this gate current here, IG. You'll have this voltage here, so this is VAK for anode cathode, and here this is a sine voltage, so it's VS sine omega t. Okay, and so what we're going to do is we're going to look at some waveforms, because we need to understand how everything is related to all the different parameters and such. So we see here that VS is a sinusoidal waveform, and that's this VS here. This maybe we can label here. Let's call this VS, okay? So that's what the source voltage is. Then you see you also have this gate pulse current. You're just applying a short pulse. And the duration of this pulse usually doesn't matter. Obviously you don't want to have a very short pulse either, but otherwise your system might just interpret that as some type of noise. But for most cases, I mean, the pulse, the length of the pulse is not critical. So what happens here is you have the same setup as a half-wave rectifier, but we've replaced the diode with an SCR. So if no gate current is applied, we know that this voltage here, VD, and I forgot to label this, VD will be 0 because this will always be 0. Okay, so if IG is set to 0 all the time, then the output voltage will always be 0 since this diode will never turn on. Okay, so the gate signal is applied at some time, or some angle, I should say, alpha, and that alpha is somewhere between 0 and pi. Okay, because that's the time where Vs is greater than 0. So when Vs is greater than 0, during this sort of region here, we apply this pulse alpha, and you see that that's obviously lined up with this here. And then what happens is, since that pulse is applied, this SCR starts to conduct, and we see that's when the output voltage VD becomes non-zero. Okay, and so again, this pulse is, I mean, it has some duration. It looks like it's kind of half, but again, it's not important. So don't interpret this as some sort of unique time or anything like that. So there's nothing unique about this time. It could be larger, it could be smaller, but again, you usually want it to, I mean, something reasonable, something manageable by your system that's sort of controlling everything. In any case, we see that this pulse is applied, and after this voltage goes to 0, we know that the current here through this resistor, if we call this, I don't know, let's call this ID, let's say. So the current that would go through this resistor would be proportional to Vs, but it would be Vs divided by R. But it would have the exact same shape, and it would cross 0 at the exact same time. And so for that reason, we see that when this crosses 0 at pi, we know that this voltage will also go to 0, and it will not become anything non-zero after that. It will remain 0 for the rest of the period. And that's because once this current reaches 0, this SCR will turn off, and you'll have a 0 voltage at the output for the remainder of that period. And then again, in the next cycle, you'll have another pulse applied at 2 pi plus alpha, which is obviously just periodically, which is, I guess, alpha just shifted by one period. So every period you would have a pulse like this, and every period you would have this sort of repeating waveform. So alpha we call the firing angle. Okay, so alpha is called the firing angle. So it's the angle, I guess, where you're, I'm sure there was some historical reason as to why they call it the firing angle. I don't know off the top of my head what this reason is, but in any case, it's the angle relative to where a diode would have turned on. So it's the angle of delay relative to where a diode would have turned on. Now, what does that mean? That means a regular diode, by regular I mean like a standard diode that would turn on at like 0.7 volts or whatever, would have turned on at 0 as soon as the volt, I mean, again, ideal diode. An ideal diode, normal diode, would have turned on at this point here. But instead, we're saying this thing turns on here at alpha. So we define alpha as whatever that phase shift delay, or whatever you want to call it, is relative to the standard sort of turning on thing. So we have the diode rectifier case is a sort of benchmark, I guess you can call it. And so everything is relative to that, right? So we can then determine what the average output voltage is, right? Because we know what this waveform is. We know this is just a sine wave, right? And we know this angle is alpha. So we can determine then the output average voltage. So VD average will be 1 over 2 pi, because 2 pi is the period. And we know that this is only going to be non-zero between alpha and 2 pi, and really it's only going to be between alpha and pi. But I mean, just for the sake of, I guess, completeness, I'll write 2 pi because I know that's the overall period. And this is going to be Vs sine omega t d omega t, right? And if you solve this integral, you'll get Vs divided by 2 pi 1 plus cos alpha, right? And so we can also define a sort of maximum output of what the diode half wave would be, right? So we're relating this to the diode, treating it as the diode case as a sort of benchmark, right? So what I can say is we can call this VD naught divided by 2 1 plus cos alpha. And I'm defining VD naught, as being, as being Vs divided by pi, because that's what the average output of a half-wave rectifier is when you have a diode. Okay, so we have this sort of, they call it a control characteristic of what how the output varies relative to the diode case, right? So we see here that when alpha equals 1, right? Or sorry, alpha equals 0, VD average over VD, well, we use this as an overbar. They've used this sort of brackets. You can treat this however you want, really. So why don't we just get rid of this and call it VD bar, right? So sometimes they define this as the average. Sometimes they refer to this as the average. It depends on the reference material that you're using. In any case, the average output voltage relative to the average output voltage of the diode case varies in this shape. So we see that when alpha equals 0, you basically have the exact same case as the standard diode, right? So when alpha equals 0, cosine 0 would equal 1. 1 plus 1 is 2, divided by 2 would be VD naught. And VD naught we know is Vs over pi. And we see then at this pi, it goes to 0. So basically what you can do is you can control the output voltage within this sort of range between 1 and, well, normalized I guess to this, between 1 and 0, right? So you have a sort of handle. You can control the output average, whereas in the diode case you couldn't. So this gives you obviously another degree of freedom. So now you can have you can implement some type of closed loop control. You can change the firing angle according to whatever the requirements are of your circuit, and you can implement more and more interesting and elaborate circuits, is really what it comes down to. More useful, practical circuits, right? So what did we do in this video? We looked at a new, well, I don't know how new it is to you. Relatively speaking, it might be new if you've never studied this stuff before. But we looked at this silicon-controlled rectifier, or thyristor it's called sometimes. We then used the thyristor in place of the diode to develop a new half-wave, well, not new, but a modified half-wave rectifier circuit. We saw from the waveforms that this firing angle alpha controls the average voltage, and we see that it's a cosine relationship here. So the cosine of alpha changes the value of the average voltage, and we saw that the average voltage can vary between whatever is the diode case and 0. Right, so either in the case where alpha equals 0, this behaves just like a regular diode. You can have it behave as anything else, or, well, I guess a modified version of that. You can scale the output voltage to anything between 1 and 0, and 1 again being the average of the SCR version relative to the diode version. It can be anything between 1 and 0. Okay, so I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.